benign overfitting, kind of continuing from what Nati was talking about in his last tutorial. And our first speaker for this afternoon is going to be Niladri Chatterji, who's a postdoc at Stanford and got his PhD here at Berkeley just last year. So really excited to hear your talk.
Thanks, Spencer, and thanks to all the organizers for organizing this really nice workshop and also for the invitation. Today, I'm going to continue talking about some results about interpolating models. So this, like Nati's talk, was a great introduction to everything I'm going to talk about. So hopefully it sets up the background really nicely. This is joint work with Tatsu, who's one of my postdoctoral advisors, Sam and Alex, who are grad students at Stanford, who are really excellent, and Phil, who's at Google Research. So the setting for the talk is these set of experiments that Nati talked about and also alluded to throughout his tutorial today morning. We've seen these set of experiments that show that deep networks tend to generalize well, even when your training data has misclassification noise. Your model is vastly overparameterized. So the number of parameters in your model is much larger than the number of data points. You're using training methods that aren't explicitly regularized, and you aren't really early stopping too early. And you're training to almost or nearly zero training loss via some gradient-based method. So these set of experiments were both surprising, and this has led to sort of many people in this room sort of trying to investigate why networks tend to generalize despite sort of seemingly overfitting to the noise. And it is a surprising statistical phenomenon. But another reason is interpolating the data is often quite beneficial. So there are multiple experiments that show that when you're in this interpolating regime, that is when you have many more parameters than number of data points, your test error is often lower, and it's actually beneficial to sort of interpolate the data. However, I should point out that like most of these sort of experimental observations are sort of in the following setting. Typically, the distribution of your training data is sort of very well aligned with the distribution of your test data. So you have no shift between the distributions from training to test time. And secondly, you're usually looking at sort of dense models that are trained by some gradient-based method on the squared or cross-entropy loss. So usually it's in this sort of standard setting of machine learning where you have no shift between your train and test data, and you're training sort of standard sort of ResNet kind of models using HGD. So what I'm going to talk about today is what happens when we veer off sort of the standard machine learning setting where we have no distribution shift and we're training dense models, and ask what happens to interpolating models there. So sort of the first sort of setting that we're going to look at is what happens to interpolating classifiers when you have a shift from training to test time. This is something that's being explored by the machine learning community quite by a lot of people over the past few years. And sort of one sort of data set that's often used is the celeb data set. So during test time, you have these common groups in the training data. So here you're trying to identify, let's say, the hair color of the celebrity, whether it's blonde or dark. And you have sort of these groups where you have lots of pictures in the training group where you have people with blonde hair that are female and people with dark hair that are male. But you also have these atypical groups in your training set where you have sort of people who are male with blonde hair, but you see a very small fraction of this in your training set. So usually your training set is an imbalanced mixture of these groups. However, you could think of a situation where, and in fact, the test set is such that it's a uniform mixture over all of these groups. So you can see during test time, you could equally likely see a sample from each of these groups. So what happens if you learn interpolating classifiers in the presence of such distribution shifts? So you could look at a loss function that tries to correct for this shift. So you could reweight sort of these atypical points a lot more, and you could train until interpolation. So the curve that we're going to look at is error versus ResNet width. And ResNet width is sort of a proxy for how many parameters that we have. We find that as we start like increasing the width and interpolating the data, the error on this worst group, so these atypical examples during test time, it starts to rise. So we see that because the error on these atypical groups is rising, the test error, the overall test error, which is a uniform mixture over these groups, is also going to rise. So we see that, and we have seen this, like people have found this across a whole bunch of settings. This is just an example I'm giving you with Celeb A. People have found this to be true across lots of training methods and data sets as well, that reweighting the cross-entropy loss is often ineffective. And in fact, to see why reweighting fails, we don't even have to look at neural networks. Here's a toy data example where I have a minority group. So these blue points are the minority group, and you have many points from the majority group, and you're trying to learn the max margin classifier, which is this dotted line. If you run gradient descent on the unweighted objective, which is just the unweighted cross entropy objective, versus whether you reweighted, you tend to learn the same classifier as you start to interpolate the data. Okay, so it seems like reweighting is seemingly incompatible with interpolation, and it's not quite clear whether we can get whether reweighting is an effective sort of robustness intervention when we are interpolating the data. So that's the first sort of path that we're going to veer off. The second thing I'm going to talk about is sparse models. So as Nati alluded to in his tutorial, again, we've been seeing sort of models that have been scaling, and again, they've been leading to sort of big gains in terms of downstream accuracy. However, this comes at the cost of added memory and inference time. As these models are getting large, even taking a forward pass through these models is getting pretty challenging. And people have started looking at sort of what happens if you train sparser models. So one example I'd like to give you from the domain of NLP is people have been training large language models that have been sort of very good over the past few years, and they're huge models, and even doing inference of them on them is sort of sometimes prohibitively expensive. So people have been looking at sort of sparse mixture of expert models, which are still large models, but are much more efficient in terms of both inference times and sort of power efficiency. So you can ask, you may want to train sparser models, but how does that sort of affect the test error? Again, I'm going to show you a plot where I have error versus the number of the width, which is going to be a proxy for number of parameters. We see as you start to train, when you start to train dense models, you see sort of the error go down as you increase the overparameterization. But as you start to learn sparser and sparser networks, the test error is definitely higher. So as you learn sparser networks, even when you're interpolating the data, the test error tends to degrade. So the next question that we ask is, if you're trying to learn sparse networks, and you're interpolating the data, are you always going to suffer higher error than if you were to learn a dense model? So those are the two questions that we're going to address. And let me give you so that's going to be the two topics that we veer off into. We're going to study both of these non-standard settings, again, with the humble linear model, and hopefully build both algorithmic insight and maybe try and draw conclusions for what's happening with neural networks. The first one was going to be about interpolation and distribution shift, and the second one explores the interplay between sparsity and interpolation. So with that, let's get started about interpolating classifiers with importance weighting. So the setting for the talk is going to be binary classification with distribution shifts. So we have n data points. The features are in RD, and the labels are binary. So they're ±1 drawn from some distribution P train. Okay. So think of like the Celeb A example, where you have many maybe examples from these common groups, but few examples from this atypical group. But your goal is to minimize the test error on a different test distribution. So your samples are going to be drawn from a different test distribution. In this case, it was a uniform mixture over these. So given that this is your goal, instead of minimizing sort of the standard logistic loss, you could try and minimize the importance weighted logistic loss. So you could, associated with sample I, you could take your logistic loss and reweight them by WI. So a standard sort of classical choice to do this is to reweight them using the density ratio between the test and train distribution. Okay, so why would you want to do this? If you reweight it in this way, then after reweighting, this reweighted loss function is an unbiased estimate of your test loss. So it seems like a reasonable thing to do. And then once you have this sort of reweighted loss, you could train up until interpolation. We've already seen with the cross entropy, this doesn't work, right? Even with linear classifiers in this example that I showed you, if you were to reweight versus not reweight, you learn the same boundary. And in fact, there's theory that shows that this fails, and you can do experiments with neural networks and also see that this is essentially, you essentially learn the same decision boundary even when you minimize the reweighted loss with neural networks. And people have also shown that early stopping or regularization sort of helps. These are results about what happens when you start to interpolate the data, but you do take different paths to that interpolant. So the question is, can we design interpolators that respond to reweighting? That is, can we sort of build overparameterized classifiers that sort of have all of the benefits that we see with overparameterization in the standard IID setting, but also have them respond to reweighting? So to do that, we first want to understand why sort of exponentially tailed losses like the cross entropy or the logistic loss fail. So we're going to consider linearly separable data, x1, y1 up to xn, yn. We're going to look at linear classifiers. So the classifier is just xi transpose theta, and we are minimizing this reweighted loss. If you look at the iterates of gradient descent with step size eta, if your step size is small enough, past sort of theoretical result shows that the direction of this classifier, like you have to look at the direction because the iterates are going off to infinity, but the direction of this classifier in fact goes to the max margin classifier. One thing to notice is this asymptotic direction does not depend on the weights wi. So you could have set these weights any way you wanted. Asymptotically, you're going to the same max margin classifier. Okay. That's a bit weird. It feels like we have set these weights in, we were hoping that these weights would have an effect, but at least while we interpolate the data, it plays no effect. So what's an intuitive way to understand this? So we have this reweighted objective. How we could sort of interpret this reweighted objective is we create sort of a new data set where we take sample I and we repeat it wi times. Let's think of wi as being an integer. So you can just repeat the sample I wi times. So now you've created this new data set, and you could, and this is like the standard loss function on that data set. You don't have to reweight it. The max margin classifier on this new data set is unchanged, right? You have repeated the constraint for the max margin classifier wi times, but that's not going to change what the max margin classifier is. And now you can just use sort of the usual implicit bias results that Nati talked about, that tell you that gradient descent with small enough step size converges in direction to the max margin classifier for the logistic loss, and conclude that reweighting also doesn't get you anything. So hopefully that conveys the intuition for why exponentially tailed losses fail. So the first proposal is to switch losses. So you can look at the proof of why sort of the implicit bias is the same, and you find that it's really down to the sort of loss function decaying exponentially quickly in the margin, and sort of the proposal is simple. If you want reweighting to work, you kind of need the loss function to decay sort of more slowly with the margin, and here we say you should have them decay polynomially. Let me quickly show you that this at least works in this sort of toy example. So in this toy data setting that I've been carrying around, when you sort of use the polynomially-tailed classifier loss with importance weighting, you recover the right boundary, and that's good. At least it works in toy examples. But what's its implicit bias, right? So let's say we have, again, linearly separable data, and now we have a loss function that we have designed differently. So it's like the logistic loss when the margin is small, but once the margin starts getting large, it decays polynomially. Here it decays as 1 over the margin to the alpha. Okay. Now, again, you run the iterates of gradient descent with small enough step size, and you find that the direction now converges to something different. This converges in direction to something we call the poly-tailed classifier, theta alpha. Here you see that it kind of does depend on the weights. So that's a good sign. So what you can think of as doing is you're fitting all data points correctly, and then you're trying to maximize the margin, trying to maximize this weighted margin. So think about if you have two groups, one is a minority group and one is a majority group. On the minority groups, you will have set Wi to be large. So on those groups, the margin, this classifier will try and make get a higher margin on those points. Okay. So at least intuitively, it feels like where you set the weights to be higher, it'll try and achieve higher margin. And I should point out that this really builds up on some really nice results by Ziwei, Matus, Miro, and Rob, where they studied the implicit bias of poly-tailed classifiers, and we adapted that here to study reweighted losses. So at least, sorry, go on.
What is alpha in the previous slide?
Alpha is, just think of it as, it holds for any alpha. So
is it related to how the tail behaves or something like that?
Yeah, alpha controls how the decay of the tail. So if you think about alpha equals 1, it says that the tail behaves as 1 over the margin.
And does the reweighting so I guess here you're talking about like gradient descent in the entire data set. Mm-hmm. Do you think even with batch gradient, reweighting won't help?
I think at least empirically, it doesn't seem to help. And I think if I understand correctly, at least for the logistic loss, I think the implicit bias remains the same when you have stochastic gradient descent versus full batch gradient descent. So at least there it won't help. Yeah.
Okay.
So the previous results that I said, where you can just invoke previous results, even if you were to invoke it for SGD, I think you'd get the same.
Is it obviously positive alpha? So you have to strip.
Yeah, you have to have.
It's not. It doesn't have to be greater than 1, or it's really like.
It doesn't need to be greater than 1. You have to ensure that the loss is convex and decreasing, and that's it. Yeah. Alpha, yeah. As long as you sort of stitch the loss together such that it satisfies that, you can have alpha being.
Oh, because you have to be conventional stitch together.
Exactly. Yeah. Yes.
Differentiability, right?
I think we need differentiability, but I'm not sure if that's crucial. But yeah, let's say we need differentiability.
I'm wondering if something like changing the exponential loss in a different way. Like, could I have done e to the minus ci's and choose, to give like a different way, right? Like, it's clear the wi in front doesn't do it. Mm-hmm. Like, is it clear that somehow a multiplicative shift inside exponential, right?
I think that
feels like more correct.
Yeah. So if you want sticking to sort of classical reweighting algorithm where you reweight the loss and you start to fiddle with the exponents of the then the implicit bias will change. I think while that would change the implicit bias, I think one thing that's trickier is how do you set sort of those exponents correctly. Yeah, and I think One, two.
C exponentiation. Yeah, like it's e to the minus.
Yeah, the smooth, the corresponding smooth loss, which is however somehow, then the both places.
I was thinking of demand larger margin for some CIs. Like the margin would be proportional to 1 over CI or something.
Yeah, I think the proposal, if I understand correctly, is to use a different CI for every sample. So you said that, yeah.
Could I just make a comment about this differentiability condition together? So in the original paper, we also we actually stitched together that it's y differentiable so that we have smoothness. But I think in terms of like actually getting the custom products to work, maybe like, you know.
Yeah. Yes.
Just a quick comment regarding the multiplicative factor. So I think at least in the linear case, I believe that depending on the margins, the ratio of the two margins that we want, we can set the multiplicative factors in that ratio and we get actual margins in that particular ratio. Like C1 and C2. C1 by C2 is yes.
Good. So right. So we have built a loss function that at least asymptotically responds to a reweighting. But you could ask, what about the test performance, right? Like we've changed the implicit bias. We've got something that depends on the weights. How does it perform? So that's what's coming next. So we're going to study a setting where the poly-tailed classifier achieves minimax accuracy, whereas we're going to show a lower bound in the same setting where the max margin classifier, what you'd get by minimizing sort of a reweighted exponentially tailed loss, fails. What's this setting going to be? It's going to be a setting where we have, it's a label shift setting. So we have two classes and a class conditional distribution corresponding to each class. So you have a majority class, let's say, that are associated with labels +1. You have the features for this majority class are drawn from a normal with, let's say, mean mu1 and variance identity. This can be sort of relaxed to sub-Gaussian distributions, but for this talk, let's just think of the class conditionals being normal. And then you have a minority class where you have labels -1, and you have features that are drawn from mu2 and mean mu2 and covariance identity. Okay, so in the training data, we're going to have skewed training data. So we're going to have a lot more samples from the positive class than the negative class. And tau is going to be the ratio between the number of positive samples by negative samples. So as tau gets larger, your training data is more and more skewed. And the test error is going to be a uniform mixture from both of these classes. Okay. We're going to make some assumptions on the data. We're going to assume n is larger than log1 over delta, where delta is the failure probability. The scale of the separation, which is norm of mu, is going to be larger than n squared times log factors. And we're going to be in the high dimensional setting where d is larger than n times norm of mu squared. Okay, and we're going to set, we're going to minimize reweighted losses. So the way that we're going to set the weights is we're going to set it equal to 1 if your sample comes from the positive class, that is if it has label 1. And we're going to set it equal to some w, which I'll specify in a moment, which is greater than 1 if it comes from the minority class. Okay. So for this model, if the loss decays as 1 over z, so we have fixed alpha to be 1 here. And if your failure probability is less than a constant, and if you set your weights in this sort of weird way where you set w to scale with tau cube, so you want to set w to scale with tau cube, which is where tau was sort of the imbalance ratio. Then with probability 1 minus delta, the test error of this polynomially-tailed classifier decreases exponentially in the number of minority group samples times norm of mu to the 4 divided by d, the dimension. Okay. This is known to be sort of minimax optimal in this problem. And you know, if this thing is all going off to infinity, your test error is going to 0. So that's an upper bound on the performance of the polynomially-tailed classifier. And further, we show that if your imbalance is sufficiently large, then with probability at least 1 minus delta, the test error of the max margin is at least a constant. Okay. So here's a setting where this could go off to infinity and the test error could go to 0. But if you use sort of an exponentially tailed loss, your test error is lower bounded by a constant. Just to instantiate this with a setting, so say norm of mu the number of samples in the minority group and tau are scaling this way with D. Don't worry about the exact exponents. This is just as an example. As D goes off to infinity and all of these sort of problem parameters are scaling appropriately, you have this sort of strict separation between the test performance of the max margin classifier and the polynomially-tailed classifier. Okay, so first thing is why set the weights this way? So I sort of specified a pretty unusual choice for the weights. So I asked you to set the weights as tau cube. That's not a standard choice. So if you think about this, if you set W equals tau cube, the resulting sort of loss that you get is biased. It's not an unbiased estimate of the test loss. The sort of classical choice that you have in sort of classical statistics tells you that you should set W equals to tau. This results in sort of an unbiased training loss. And further, there's nothing special about tau cube. I should point out that if L scales as 1 over Z to the alpha, then you have our theory prescribes a different setting for W in terms of alpha. So we're going to dig deeper into why we set W this way. Firstly, let me just show you in this setting that W equals tau cube is maybe the right way to set the weights. So I'm going to show you some simulations where I'm going to show you the test error versus the imbalance ratio. So as the imbalance ratio gets larger, the problem is getting harder. You can look at the performance of the max margin classifier and the polytailed classifier when you don't have any importance weighting, and the test error gets larger as you'd expect. Secondly, if you use the polytailed classifier, but you use sort of the classical importance weights, you see that the test error is definitely lower, but it is still rising as sort of the imbalance gets worse. And finally, when you set W equal to tau cube here, your test error essentially remains flat as your problem gets harder. Another way to see this is you look at the test error versus rho, where rho is this exponent of tau. So we're going to set W equal to tau to the rho. We can look at the decomposition between minority group error and the majority group error. So the light blue line shows sort of the test error of the minority group samples. And we see that like even when we set it equal to tau, your minority group samples suffer higher error than you'd want it to. Whereas when you set it equal to tau cube and really overcorrect on these minority group samples, you suffer low overall error. So hopefully this simulation is convincing. Next, I'd like to step through just sort of the key ingredients of the proof to maybe convince you that why we get this W equals tau, and also point out some ideas that we had to use. Firstly, by Hoeffding's inequality, you get that the test error at infinity is upper bounded by these quantities that involve what we call the normalized margins. Yes, sorry.
If you change the the sweet spot,
you change the what? Sorry.
If you change the data set, if it's another data set that you're using, but the same, you vary it similarly, will you get some other W, some other row that is very good for your
it depends how you change the data set. Yeah, typically yes. So in sort of real experiments that I'll show you later, that's a hyperparameter that we choose off the validation set. I don't think we tried simulations where we varied these toy distributions around, but my guess would be it may. But I think the important thing to take away is that we never found that the classical importance weights of setting W equals tau was kind of the right thing. We always had to overcorrect. Right. So the test error, we're looking at the test error, and we see that you can bound it in terms of these normalized margins, which essentially is the inner product between theta and the means mu1 and mu2 divided by norm of theta squared. So if sort of we could track how these normalized margins evolve, we could sort of get a bound on the test error. You can sort of write down how these normalized margin evolves as a function of t, which is the iteration count. And you see sort of two things. One is the red term here kind of is the right quantity. If we could show that this blue term that we have here in a bracket, if this is a constant, we'd kind of be done, because then we'd have showed that the normalized margin is lower bounded by the number of minority group samples times the signal strength by square root t. And that's kind of what we want to get our upper bound. And to do this, we kind of need to show that this blue term is constant, we kind of need to show that the numerator is lower bounded. So the key sort of ingredient to show that this numerator is upper bounded is what we call the loss ratio bound, which sort of is useful in a variety of problems apart from this one, which kind of shows the following. It shows that if the step size is small enough, then for all iterations S of gradient descent, for all sample pairs I and J, the ratio of the losses is upper bounded by some constant times the inverse ratio of the weights on those points, raised to a third. Okay, so if you think about what this is telling you, it's telling you that if your samples are coming from the same group, then the losses of those samples sort of reduce at the same rate as training goes on. And if your samples come from differing groups, then it's bounded as a function of the weights on those groups. And essentially, if you sort of use this loss ratio bound to lower bound the numerator and do a bit of algebra, you can show that the numerator is lower bounded by some function of the denominator. So the crucial thing I want you to take away is if you can show that the loss ratios are bounded, that is your training algorithm reduces the loss on all points equally, you can sort of plug that in and show bounds on the normalized margin. So we did a bunch of sort of theory with linear models, and we found sort of two things. One is using polynomially-tailed losses, and the second was overcorrecting with the importance weights. We could see how this translates to sort of experiments with neural networks. Firstly, if you look at sort of interpolating models and we look at the Celeb A data set, we see that firstly, if you use polynomially-tailed losses compared to the cross-entropy loss, you definitely see sort of gains in accuracy. And secondly, if you exponentiate the weights, you see sort of the gains improve further, even as you start to interpolate the data. Whereas for the cross-entropy loss, sort of the accuracy essentially remains the same, whether you reweight or don't reweight, as sort of theory kind of predicts. Yeah. Sorry. Early stopping does help. So that's exactly the next plot here. So if you do early stop, you see sort of using the cross entropy loss does lead to better accuracy. But often like using the polynomially-tailed loss and early stopping helps even further. So early stopping still does help, but like switching to the polynomially-tailed loss still seems to help. And so this was comparisons with cross entropy loss. There are other sort of stronger reweighting methods that people have proposed in the literature. Yes.
If you go back to the last slide, did you try early stopping with Celeb data set?
Yes. Yeah. So this is like, I'm showing you, that was for Celeb A, this was for CFAR. Yeah, we do have experiments with Celeb A and well, and like the trends are similar. Yeah, you can compare to other stronger reweighting baselines that people have proposed for these group shift problems. We find that like it's almost always as good or better than other sort of reweighting methods proposed. And finally, I'd also want to say that there are other more sophisticated sort of distributionally robust optimization methods that people have proposed, and you can plug in the polynomially-tailed loss into that, and you also see gains in accuracy. So with this, I'd like to finish the first part and just highlight the takeaways. One is sort of robustness interventions behave quite differently in the interpolation regime. So sort of importance weighting doesn't help for the cross entropy loss once you start interpolating the data, but it does help if you use the polynomially-tailed loss, and sort of studying this theoretically and figuring out the right implicit bias is useful. Finally, sort of careful theoretical analysis, even with toy models, often can lead to non-intuitive algorithmic ideas. And at least in this case, we found that it was useful and translated over to neural network experiments as well. Yes.
I still don't quite understand the intuition for exponentiating.
I mean, so I guess the idea is, if you look at the like the test error, you find that the losses on sort of you essentially want like the losses on the two groups to reduce at the same rate so that they influence your classifier the same amount as training goes on. So that was what the loss ratio bound was showing. It was bounding how much the loss on sample from one group compares to a loss from sort of.
I thought it was the gradient.
The gradient should be equal, and here it's like the loss is related to the gradient.
Okay.
Yeah. So yeah, you can think about the gradients to be equal or the loss. Yeah. Essentially, yeah, you want like the losses to decrease at the same rate, so that like, so imagine if the losses on the minority groups were to reduce too quickly, then late in training, all your classifier would only learn from the majority group points. If you just look at how the gradient, if your loss is too small, it won't like influence how the classifier is updated. So essentially keeping the loss ratio roughly constant helps. You want to keep it constant across the entire group. Yeah. Yes.
Modify this for like, if you have like here, it's a binary class problem. So you have one ratio and you got it into the.
I think in terms of the theory, it should be sort of, I mean, we didn't try it, but I expect you can sort of take this model, create a multi-class version and sort of proceed. We didn't try multi-class sort of neural network experiments. So I'm like, no, if that's the question, I'm not sure what's the right way to select the weights, but I'd probably guess off of val side. Yeah. Okay, so that's the first part of the talk. Second, I'm going to talk about sort of the interplay between sparsity and interpolation. So just to remind you, we have seen these experiments where you can interpolate the data, and if you have a sparser model, the test error seems to be higher. Again, we're going to try and understand this with linear models, and we're going to study sparsity in linear regression. So here the setting is going to be the following, where we have n data points. Y's are now not labels, they're sort of reals. We're going to be in a setting where xi is d-dimensional, where d is much larger than n. So you're in the overparameterized regime. And the y's are related to the x's as follows. So you have a true theta star. So y is equal to xi transpose theta star plus some noise. And we want to think of a setting where theta star is k-sparse. So the underlying truth is k-sparse. And we want to think about, are there interpolants that can sort of leverage this underlying sparsity? So how we are going to do this is ask us the following questions. We want to ask, how does the excess risk of a sparse interpolator behave? So a canonical sparse interpolator to keep in mind is the minimum L1 norm interpolant. It's literally you minimize the L1 norm subject to fitting the data. This is also called basis pursuit, and as Nati, I think, briefly talked about it in the tutorial, this is known to sort of promote sparsity, and there's decades of literature on this. So that's a canonical sparse interpolator to keep in mind. And you could ask, how does this sparse interpolant compare to sort of dense interpolants? So if you think about the minimum L2 norm interpolant, it's likely to be dense. We have sort of bounds on the excess risk of the minimum L2 norm, and you could ask how does the excess risk of the minimum L1 norm compare to it? Given that I have posed 2 questions, I better have an answer. So we kind of show that sparsity is in fact incompatible with interpolating noisy data, and we show this via a lower bound on the excess risk. How do we construct this lower bound? So say you have these data points generating in this way. We're going to assume that the coordinates of the covariates are drawn from a normal distribution with 0 mean and covariance sigma. Sigma is going to have this very particular structure, which we call the K epsilon model. So you have K, it's going to be diagonal. Your first K directions are going to have variance 1. Your last D minus K directions are going to have variance epsilon. And think of epsilon as being smaller than 1. So it has this very nice sort of spike structure. The noise is drawn independently of the data, and it's drawn from a normal with 0 mean and variance sigma squared. And the true model is K sparse, right? Yes.
Stable, you have like a positive result about the L1 interpolant?
I don't, but like people in this room do. Yeah, at least with isotropic covariance, there are a bunch of like really nice results.
What was the question?
Sorry, do you want to?
I mean, this is like essentially saying that you're like low dimensional, right? And you have some, it's a bit like all the way to be like a d-dimensional covariance. So like if the metric is like isotropic, does the L1 interpolant doing well?
Maybe we can look at the lower bound and like maybe that will make it clear. So here's a lower bound for the excess risk, and this is a lower bound for any sparse linear interpolator. So if the failure probability is a constant, if the noise variance is sort of comparable to the norm of theta star, and D is larger than N and N is larger than K, which is the sparsity raised to the 1 plus constant, then with probability 1 minus delta for any S sparse interpolant, the excess risk of it is lower bounded by sigma squared N divided by S log squared D over S. Okay. So the excess risk here is for this problem is just theta of S minus theta star, which is this true underlying model, measured with respect to this sigma norm squared. We see as your model gets more and more sparse, so this lower bound gets larger. So your excess risk could be larger, is lower bounded by something larger. And in the numerator, you have sigma squared N, which you could think of as how much noise do you have in your training data. So it's essentially saying your excess risk is at least sigma squared N divided by S. And I should also mention that there was a similar lower bound derived by Muthukumar et al. In the isotropic case where epsilons are just 1. So just to sort of flesh out what this bound is telling us, so you could have sparsity levels starting from K, which is the sparsity of the underlying model, N and D, where D is just corresponding to the sparsity of a dense model. This lower bound says that the excess risk of the sparse model is lower bounded by something larger than the excess risk of a dense model. Yeah. So what does this mean about the minimum L1 norm interpolant? We know that in this setting, basis pursuit outputs an N sparse solution almost surely. This is, you can look at one of the many papers in the literature, and this is a fact about the basis pursuit that's known. So if you can plug this, if your S is equal to N, this tells us that the excess risk is lower bounded by something that's sigma squared divided by log D over N. So it's only decreasing logarithmically in D. So you can think of D growing, and this is only going down logarithmically. And Okay, so why is this bad? So consider a case where I set the parameters of the problem in this way, and this is an example. So I can set the sparsity level to be square root n. I could set d equals n squared. Could set epsilon, which is like the variance of the small directions, as 1 over n squared. And I could set like the noise variance and theta star as a constant. This says that sort of previous results tell us that the risk of the OLS solution, or the minimum L2 norm solution, goes down as 1 over n in this case. However, for the minimum L1 norm solution, it's lower bounded by something that's logarithmically in. It just goes down logarithmically in n. Okay. In fact, even though the ground truth is sparse, the risk of the L1 norm interpolant can be exponentially worse. Yes.
Is there a lower bound for the OLS, and is there an upper bound for the L1 norm interpolant?
For the OLS, yes. So in this paper that I sort of cited here by Peter, Alex, Gabor, and Phil, they have a lower bound, at least on the variance of the estimator, and at least actually there are upper bounds for the L1 norm solution. There are upper bounds for the minimum L1 norm solution in the isotropic case by Nati and Friedrich and Lijua and Danica and Constantine and Fanny and co-authors also. Yeah, so there are upper bounds in multiple settings that all sort of go down, I think, logarithmically in n. In the isotropic case, I think the upper and lower bounds almost match up to sort of, I think, a square root log n factor, but yeah. Cool. So yeah, and let me just spend like a quick slide on the intuition before yeah. So the energy of the noise scales as sigma squared n. So we know norm of y squared scales as sigma squared n because you have n independent sort of noise. You have noise added to each sample. Dense interpolators sort of can spread this over d directions. So if you think about the interpolation equation, you need to have y is equal to x theta. For the OLS, you can spread this over many unimportant directions, and this is kind of the intuition that's sort of baked in and talked about in these papers that derived the upper bounds. You can sort of spread the effect of the noise in these many unimportant directions. You can fit the noise using these directions, and it doesn't hurt you in terms of the risk. However, if you look at sparse estimators like basis pursuit, it can only use a smaller number of directions to sort of hide this noise, which is why it suffers higher risk. Okay, so I finally want to end with just a summary and highlight some open questions. Firstly, we talked about importance weighting and interpolation. We saw that robustness interventions tend to behave in weird ways in the interpolation regime, and it's sort of interesting to sort of design algorithms that sort of work in this regime. And also that sometimes the solutions can be non-intuitive, like in this case, we had to have weights that were exponentiated and needed loss functions that were biased. We also talked about the interplay between sparsity and interpolation. It's, I think, sort of interesting to ask if there are other properties like sparsity that are either aligned or misaligned with generalization in this regime. And finally, I mean, I showed sort of experiments with neural networks where seemingly sparsity is harmful. We showed lower bounds with linear models, and I have no clue how to prove this for neural networks, but it'll be interesting to understand if sparsity is also sort of fundamentally harmful when you are fitting noise with neural networks. With that, I'd like to thank my collaborators once again, Tatsu, Sam, Phil, and Alex, and yeah, happy to take questions.
So thank you for the talk. Niladri, we have some time for questions if anyone has any.
So what role does the mean function play in the sparsity analysis? I didn't see like k appear anywhere in the lower bound, but I assume you're hiding some dependence of the results on the mean function just in the foundation. The mean being linear is
What do you mean by the mean function?
the conditional mean of y given x. So in this case, that would just be the fact that the true coefficients are the k-sparse. Where does that come into play in the results?
I guess, I mean, k is sort of smaller than n here. That's kind of where we use it. Apart from that, it's sort of, it doesn't really appear anywhere else in some sense.
So I guess it's tied to the covariance. That's probably another key here, right?
In fact, yeah. So I mean, so in fact, like the covariance is designed so that sort of theta star is non-zero only in the directions where the covariance is large. So we align, so theta star is k-sparse in that top k subspace where the covariance is large. So that it's somewhat easier to recover sort of that theta star effectively. So in that way, yeah, the theta star is sort of k-sparse in the top k direction. Yeah, I didn't mention that, but in the construction, that's how sort of theta star is constructed.
I'm trying to get a sense for how kind of fundamental it is for k to be, let's say, tied to the covariance in this way, and also for k to be small, because the intuition doesn't really have much to do with the particular, right? The intuition was somehow more broadly about the estimator suffering from a lack of ability to spread noise among the portions.
Right, and essentially that's where, so that's sort of I'm trying to think if there's yeah, I mean, essentially that's where the intuition for the lower bound sort of comes in. So you kind of have to, so if you think about any estimator, it has to predict well on so if you look at the risk, given that sigma is sort of large in the top k directions, it kind of has to get theta star correct in those top k directions. Otherwise, it's going to suffer high excess risk. So either sort of you could predict theta star well in those top k directions. Otherwise, you suffer high excess risk, or you will have sort of really large directions in those in the final d minus k directions, which contribute to the excess risk. I'm not sure if that sort of answered your question, but yeah, happy to chat and sort of go through it more carefully.
Any other questions?
Weighting. What about regression? Can you do there? That seems trickier to play these tricks. Can you do something there?
With regression, yeah, it seems tricky because really, I mean, yeah, I mean, what's crucially used in all of these results are that like your direction is going off to infinity. If you're, it seems like technically like a challenge, but actually it's a boon here in some sense that you in regression, there are results that say that at least for some class of losses, any reweighting schemes fail as you start to interpolate the data. And we thought about it, but yeah, we didn't have any good answers to fix that. Yeah.
Last question. Okay, let's thank you here again. Last talk for today will be at 4 o'clock.